And now in this lecture we will find out the area of rectangle ABCD using two different methods. In the drawing we have the semicircle, this is semicircle, and rectangle ABCD. This is line segment AM, that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So we start with the first method. First of all the angles inside rectangle ABCD are right angles. So all those four angles are right angles. This is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. In the next step, we will define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. Point O is the center of the circle, point A is the point on the circle itself, therefore OA is the radius of this circle, that's equal to x according to our definition. We define the point of tendency of tangent DC with this circle. This point is point E. And we'll join points O and E together by a straight line. Point O is the center of this semicircle, point E is the point on the semicircle itself, therefore OE is the radius of this semicircle. It is equal to x according to our definition. The radius OE is equal to x. The radius OE is drawn from point E. This is the point of tendency of tangent DC with this semicircle. And whenever you have radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO according to rule 1. If DC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So actually, inside quadrilateral ADEO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees. According to the rule, it states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral AEOA we have 4 right angles. And according to rule 5, any quadrilateral that does 4 right triangles must be this left triangle not a square. So we relate to quadrilateral DEOA is a left triangle because it has 4 right angles. But we also know that the opposite sides of a left triangle are equal to each other. So in left triangle DEOA, side OE equals to the opposite side AD. But OE is x, therefore AD must be also equal to x units in its length. We define the length of this line segment OB as A. In the next step, we join points O and M together by a straight line. We define this line segment BM as B. And we implement the Pythagoras theorem on this right triangle MOB. According to the Pythagoras theorem, in any right triangle, the square they produce equals to the sum of the squares of the perpendicular. So I will copy the right triangle OMB in the new page, and we will implement the Pythagoras theorem on this right triangle OMB. Here by PT is the progression for Pythagoras theorem. So this is the right triangle OMB that are coming from the original drawing. According to the Pythagoras theorem, in this right triangle OMB, or M squared, that is the square of the hypotenuse, is equal to MB squared plus B all squared. So write it down. So OM squared, that is the square of the hypotenuse, is equal to MB squared plus OB squared. But before that, what is the definition of line segment OM? Line segment OM starts from point O, that is the center of the circle, and ends at point M, that is the point of the circle itself, on the semicircle itself. So this is exactly the definition of a radius. Therefore OM is the radius of the circle that is equal to x according to our definition. So OM equals to x. So according to the Pythagoras theorem, OM squared equals to MB squared plus OB squared. OM is x, therefore OM squared is x squared. And it is equal to MB squared. MB is B, therefore MB squared is B squared plus OB squared. OB is A, therefore OB squared is A squared. So in total, according to the Pythagoras theorem, we actually found out that x squared equals to A squared plus B squared. In the next step, I'll copy the right triangle, the right big triangle line A and B in the new page, and we will implement the Pythagoras theorem of this big right triangle A and B. So actually, this is the right triangle MBA that I call it from the original drawing according to the Pythagoras theorem. This right triangle MBA, MA square, that is the square of the hypotenuse, equals to MB square plus BA square. So I write it down. MA square, that is the square of the hypotenuse, MA square equals to MB square plus AB square. MA is 5, therefore MA square is 5 squared, that is 25. And it is equal to MB square. MB is B, therefore MB square is B square plus AB square. AB is X plus A, therefore AB in total is X plus A. So AB is X plus A, therefore AB square is X plus A square. So in total, according to equation 2, I shall find out that 25 equals to B square plus X plus A square. So 25 equals to B square plus X plus A square. X plus A square equals to X square plus A square plus 2 times X times A. In this side of this equation 2, we have A square plus B square. According to equation 1, A square plus B square equals to X square. Here, A square plus B square, according to equation 1, equals to X square. Therefore, we can substitute A square plus B square in this equation 2 by X square for this equation 1. We'll do it now and we'll get that according to equation 2, 25 equals to, again, B square plus A square is X square according to equation 1, plus X square plus 2AX. So 25 equals to X square plus X square is 2X square plus 2AX. Here we divide this equation 2 by 2, and we get that according to equation 2, we have 25 over 2 is 12.5, so 12.5 equals to 2x square over 2 is x square plus 2ax over 2 is ax. So in total, according to equation 2, we actually found out that $12.5 equals to x square. Again, here, x square, 2x over 2 is x square, and 2ax over 2 is ax. Again, 2ax over 2 is ax. Okay, so we found out that 12.5 equals to x square plus ax. So here we take x as a common factor for this expression, and we get that according to equation 2, 12.5 equals to, so x is let's taken as a common factor, so inside the brackets we will have here x plus a. So in total, according to equation 2, we actually found out that x times x plus a equals to 12.5. Our mission is to find out the area of this rectangle ABCD. Again, our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? The area of any rectangle equals to the length of the rectangle times the width. The width is DA, the length is AB, and therefore the area of triangle of rectangle ABCD must be equal to DA times AB. So the area of rectangle ABCD equals to DA, that is the width of rectangle ABCD, times AB, that is the length. So in total, the area of rectangle ABCD equals to DA times AB. DA is X, and AB in total equals to X plus A. AB in total equals to X plus A. So in total, if you found out that the area of rectangle ABCD equals to X times X plus A. But according to equation 2, X times X plus A equals to 12.5. So here X times X plus A according to equation 2 is equal to 12.5. So if you found out that the area that we are looking for in this question, the area of this rectangle ABCD is equal to 12.5 square units. That is the answer to the question. I repeat again. If we found out that the area of this rectangle ABCD is equal to 12.5 square units. So we finished with the first method. In the next step, I will present to you how to find out the area of this rectangle ABCD according to the second method. So, ABCD, we know that all those four angles inside rectangle ABCD are right angles. So, this is a right angle. This is also a right angle. This is also a right angle. And finally, this is also a right angle. We have already found out that if we define the radius of this semicircle as x, then AD is equal to x. So I will not repeat on the process. We have already proved that if the radius of this semicircle is x, then AD also equals to x units in its length. So AD is x according to what we have already found out in the first method. In the next step, we'll define the radius of this semicircle as O. So point O is the center of the circle, point A is the point on the semicircle itself, point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle, that is equal to x according to our definition. We define the length of this line segment OB as A. We define this point as point M. In the next step, we will join points M and N together by a straight line. Actually, by joining points M and N, we can do peripheral angle AMN. This is peripheral angle MAN. Again, by joining points M and N together by a straight line, we can do peripheral angle AMN. Peripheral angle MAN subtend on AM. Again, peripheral angle AMN subtend on AN. And AN is the diameter of the semicircle, and according to rule 5, any peripheral angle that is subtend on the diameter of the semicircle must be equal to 90 degrees in its size. So I'll repeat quickly on rule 5. According to rule 5, any peripheral angle that is actually we have the rule that says that any peripheral angle that is subtend on the diameter of the circle or a semicircle must be equal to 90 degrees in its size. And therefore, peripheral AMN that is subtended on AN, that is the diameter of the semicircle, must be equal to 90 degrees in its size. So we define this angle alpha. So in the big right triangle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this perpendicular angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha, 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Okay, likewise, we focus on this right triangle A and B. In this right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this perpendicular angle must be equal to 90 degrees minus alpha. We are talking about angle AMB. Angle AMN equals to 90 degrees, but angle AMB is smaller. Angle AMB is smaller than angle AMN. And angle AMN equals to 90 degrees minus alpha. According to the rule, the sum of the angles in any triangle is equal to 180 degrees. Here, alpha plus 90 degrees minus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we will prove that the right triangle AMB is similar to the right triangle AMN. Okay? So, I will copy those two right triangles in a new page, and we will prove that those two right triangles are similar to each other according to angle similarity rule. Actually, it is very easy to see it from the drawing itself, but we'll prove it anyway. Okay, those are the two right triangles AMN and AMB that I formed from the original drawing. So in the next step, we prove that those two right triangles are similar to each other according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those triangles are both equal to 90 degrees and therefore they are equal to each other. So okay, this is angle MBA. In the right triangle AMB, and it is equal to this angle, that is actually angle MAN. In the right triangle AMN, they are both equal to 90 degrees and therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. So here this is angle MAN. In the right MAB, this is angle MAB. In the right triangle AMB, again this is angle MAB. In the right triangle AMB, and it is equal to this angle, this is actually angle MAN. In the right triangle AMN. They are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle AMB. In the right triangle AMB, and it is equal to this angle, it is actually angle MNA. In the right triangle AMN. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the triangles in this right triangle AMN are correspondingly equal to all the triangles in this right triangle AMB, therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually proved that this is the right triangle AMN, and it is similar, this is the sign of similar to this right triangle AMB. According to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AM, actually it is given us in the question that side AM equals to 5 units in its length. We have already found out that side AB in total equals to x plus a. AN is the diameter of the semicircle. If the radius of the semicircle equals to x, the diameter must be twice as big as the radius that is x. So if the radius is x, the diameter must be equal to 2x. So AN equals to 2x units in its length. This is the diameter AN. It is equal to 2x units in its length. It is twice as big as the radius that is x. So AN equals to 2x units in its length. So from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AM in this right triangle AMB over side AN in this right triangle AMN is equal to side AB in this right triangle AMB over side AM in this right triangle AMN. So I'll do it again. We will derive the side AM in the right triangle AMB over side AN in the right triangle AMN equals to side AB in the right triangle AMB over side AM in the right triangle AMN. AM is 5. Here AM is 5 over AN. AN is the diameter of the semicircle, that is 2x. And it is equals to AB. AB is x plus a over AM. AM is 5. AM is 5. So total, according to equation 1, we shall find out that 5 over 2x equals to x plus a over 5. Here we of course multiply this equation 1, and we get that 5 times 5 is equal to 2x times x plus a. 5 times 5 is 25, so 25 equals to 2 times x plus a. Here we divide this equation 1 by 2. So we get that according to this equation 1, x times x plus a equals to 25 over 2 is 12.5. So in total, according to equation 1, we actually found out that x times x plus a equals to 12.5. Our mission is to find out the area of this rectangle ABCD. Actually, the area of any rectangle equals to the length of the length times the width. Okay. So, our mission is to find out the area of rectangle ABCD. And the area of a rectangle equals to the length of the rectangle times the width. The width is dA, that is x. Again, the width is dA, that is x. Times the length. The length is AB, and AB in total equals to x plus a. Again, AB in total equals to x plus a. So actually found out that the area of rectangle ABCD, that is the area that we are looking for in this question, is equal to x times x plus a. But we have already found out that according to equation 1, x times x plus a equals to 12.5. So here, x times x plus a equals to 12.5. That is to say, we have found out that the area of rectangle ABCD equals to 12.5 square units, exactly as we found in the first method. So we can summarize and say that in both methods, we found out that the area of this rectangle ABCD is equal to 12.5 square units. So in the next step, I'll summarize the lecture. We'll start with the first method. In this lecture, we found out the area of this rectangle ABCD using two different methods. So in the drawing we have a rectangle ABCD and this semicircle, and we know that this is line 7 AM is equal to 5 minutes in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, because of the fact that ABCD is a rectangle, all those 4 angles inside rectangle ABCD are right angles. We define the center of this semicircle, this point is point O. We define the radius of this semicircle as x. So point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of the semicircle, that is equal to x according to our definition. We define the point of tendency of tangent DC with this semicircle, this point is point E. In the next step, we join points O and E together by a straight line. Again, point O is the center of the semicircle, point E is the point of the semicircle itself, therefore OE is the radius of the semicircle, that is equal to x according to our definition. Because of the fact that the radius OE of this semicircle that is equal to x, the radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If this is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So, those 2 angles, they are right angles because there are 2 out of 4 angles of rectangle ABCD, and all the angles in rectangle ABCD are right angles, and this angle equals to 90 degrees according to rule 1. So in total, in quadrilateral DEOA, inside this quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4th missing angle, in total it must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4th missing angle must be equal to 90 degrees in its size. So inside quadrilateral DEOA, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a right angle, if not a square. So we have to quadrilateral this quadrilateral DEOA is right angle because it has 4 right angles. But we also know that the opposite sides of right angle are equal to each other. So in right angle DEOA, side EO must be equal to the opposite side DA. But EO equals to x, therefore DA must be also equal to x units in its length. Okay, actually we will need will not prove in the second method that dA is equal to x because we have already done it right now. dA equals to x units in its length, and x is the radius of the circle, of the semicircle. Okay, so in the second method we will not prove that dA equals to x because we have already done it here in the first method. So dA equals to x, and x is the radius of this semicircle. Okay, so in the next step, we join points O and M together by straight line. Point O is the center of the semicircle. Point M is the point of the semicircle itself. Therefore, OM is the radius of the semicircle that is equal to x according to our definition. In the next step, we define this line segment OB as A, and we define this line segment MB as B, and we implemented the Pythagoras theorem in this right triangle OMB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle OMB that according to the original drawing. According to the Pythagoras theorem, in this right triangle OMB, OM squared, this is the square of the hypotenuse, equals to OMB squared plus BO squared. OM squared plus OMB squared plus BO squared. OM is x, therefore OM squared is x squared, and it is equals to MB squared. MB is B, therefore MB squared is B squared, plus OB square. OB is A, therefore OB square is A square. So in total, if we found out that according to equation 1, x square equals to A square plus B square. In the next step, I copy this right triangle A and B in the new page, and represent the bottom also with this right triangle A and B. Okay, this is right triangle A and B that I copied from the original drawing. According to the second story of this right triangle A and B, MA square, that is the square of the hypotenuse, equals to MB square plus BA square. MB is 5, MA is 5, therefore MA square is 5 square, that is 25, and it is equal to MB square. MB is B, therefore MB square is B square, plus AB square. AB is x plus A, therefore AB square is x plus A square. So in total, according to equation 2, I can find out that 25 equals to B square plus x plus A square. So 25 equals to B square plus x plus A square. X plus A square equals to x square plus A square plus 2 times A times x. So in this side of the equation, this equation 2, we have the expression B square plus A square. According to equation 1, B square plus A square equals to x square. Therefore, we can substitute B square plus A square in this equation 2 by x square in this equation 1. We did it. We found out actually that 25 equals to B square plus A square is x square plus 2ax. So here 25 equals to x square plus x square, that is 2x square plus 2ax. So in total, according to equation 2, we found out that 25 equals to 2x square plus 2ax. Here we divided this equation 2 by 2. And finally found out that according to equation 2, (25 over 2 is 12.5, and 2x square over 2 is x square, 2ax over 2 is ax. So in total, according to equation 2, we found out that 12.5 equals to x square plus a square. Here we took out x as a common factor for those two expressions. So inside the brackets, we left with only x plus a. So in total, according to equation 2, we actually found out that 12.5 equals to x plus a. Our mission is to find out the area of this rectangle ABCD. So the area of any rectangle equals to the length of the rectangle times the width. So the area of the rectangle ABCD must be equal to AD, that is the width, times AB, that is the length. Again, the area of the rectangle ABCD must be equal to the width, that is DA, times the length, that is AB. AD equals to x, AB in total equals to x plus a. Again, AD equals to x and AB equals to x plus a. So in total, we actually found out that the area of the rectangle ABCD equals to x times x plus a. But according to equation 2, x times x plus a equals to 12.5. So we can substitute x times x plus a by 12.5. So in total, we found out that the area of this rectangle ABCD equals to 12.5 square meters. We finish with the first method. In the next step, I present to you how to find out the area of this rectangle ABCD according to the second method. So first of all, we know that all the angles inside rectangle ABCD are right angles, so those 4 angles are all right angles. We define the center of this semicircle, this point is point O. We define the radius of this semicircle as x, so point O is the center of the circle, point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle, that is equal to x according to our definition. We have already found out that in the first method, the dA equals to x. Okay. In the next step, we join points M and N together by a straight line. By joining points M and N, we can then here peripheral angle NMA. Because of the fact that this is peripheral angle NMA, that is subtended on NA, that is the diameter of the semicircle, and we have the rule that says that any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in its size. Therefore, this is cofactor NMA that is subtended on the diameter AN of the semicircle, and therefore must be equal to 90 degrees in its size. Okay, so in the next step, actually, we define this side segment OB as A. Then I copy this right triangle AMN and this right triangle AMB in a new page, and prove that those two right triangles are similar to each other according to angle similar to rule. So actually those are the two right triangles AMN and AMB that are coming from the original domain. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha. This is a common angle that belongs to both triangles, so we can find out that angle alpha equals to itself, or this angle equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I should prove that all the three angles in this right triangle AMN are correspondingly equal to all the three angles in this right triangle AMB, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AM in this right triangle AMB, or side AN in this right triangle AMN is equal to side AB in this right triangle AMB, or side AM in this right triangle AMN. So again, we derive that AM or AN equals to AB over AM. AM is 5, AN is 2x, which is the diameter of the semicircle that is equal to 2x, AB is x plus A, and AM is 5. So to according to equation 1, we shall find out that 5 over 2x equals to x plus A over 5. Here of course multiply this equation 1, and finally found out that 5 times 5 equals to 2x times x plus A. 5 times 5 is 25, so 25 equals to 2x times x plus A. Here we divided this equation 1 by 2, and finally found out that 25 over 2 is 12.5, and this is equal to 2x over 2 is x, which is x times x plus A. So in total we found out that according to equation 1, x times x plus A equals to 12.5. Our mission is to find out the area of this rectangle ABCD. Okay. Actually, the area of the rectangle equals to the length of the rectangle times the width. The area of the rectangle equals to the length times the width. The length is AB, the width is DA, and therefore in total the area of the rectangle ABCD equals to DA times AB. Okay, but the DA is x and AB is x plus A. Again, DA is x and AB is x plus A, so in total the area of the rectangle ABCD equals to x times x plus A. But according to equation 1, this equation 1, x times x plus A equals to 12.5. Therefore, we can substitute x times x plus A in this expression by 12.5. So we did it, and we found out again that x times x plus A is 12.5 units according to equation 1. So in total, in both methods, we found out that the area of this rectangle ABCD is equal to 12.5 square units. Okay, thank you very much.